Now we'll discuss about elastic potential energy stored due to elasticity. About this section, we can write when a solid is elongated by an external force, we can see some work is done in this process, and a part of this work is stored as a potential energy, which we term as elastic potential energy in the material, due to which restoring forces exist. Or we can say when a solid is elongated, restoring forces opposes the elongation, and due to that opposition, restoring forces are doing negative work, and hence these are absorbing energy which is stored as potential energy or elastic potential energy in the material. Like for an example, say we are having a rod, and one end of the rod is clamped, it is fixed, and other end is pulled out with a force F. So it is of length L, and say we elongate it by a further distance X. In this situation, if the rod is elongated by X, by the definition of Young modulus of rod, we can write Young modulus is force upon the cross-sectional area of rod. Say if its cross-sectional area is given as A, this F upon A divided by the strain in this will be X upon L. So in this situation, we can directly get the value of X, which can be written as FL upon YA. This is the value of elongation in the rod. Now in this situation, if you just have a look carefully on this expression, this can be rewritten as F is equals to YA by L into X. That means if the elongation in rod is X, at equilibrium the external force required to maintain the elongation is YA by L into X, or this force is directly proportional to X. This is the situation as if the rod is behaving like a spring having force constant equal to YA by L, so that if it is having an elongation X, the restoring force on it will be Kx. So in this situation for the rod we can say equivalent force constant of rod as if it is behaving like a spring is this equivalent force constant can be written as YA by L. This itself is a very good and important concept for future. You should keep in mind that rod can be treated like a spring with equivalent force constant YA by L. And if its force constant is taken as YA by L, and if the rod is elongated by a distance X, we can say that it will also store some potential energy. So we can say at elongation X, potential energy stored in rod is this U can be written as half Kx square, which we already studied. That if there is a spring having force constant K is elongated by X, the total potential energy stored in the spring is half Kx square. So if we substitute the values, this will give us half K can be written as YA by L multiplied by X, we can write as FL by YA whole square. On simplifying this expression, this will give us half F square L by YA. This is the expression for potential energy stored in the material of rod, and this we have calculated by its equivalent analogy like a spring. We can also calculate the energy density in the material of rod as the whole energy is stored within its volume only. Let's see that also. In continuation, let us discuss about the density of elastic potential energy in the material. This density can be simply written as potential energy stored divided by volume of the material. This is expressed by the letter U, small u, E. And as we have just discussed the potential energy in the previous case, we have calculated as half of F square L by YA divided by the total volume of rod we can take as EL. So this will be written as half of F square by A square multiplied by reciprocal of Young modulus. And as we already know, F by A can be written as stress. So this can be written as half of stress in the material square divided by Young modulus. That's the expression of elastic potential energy density. And we also know that Young modulus can be written as stress by strain. So this elastic potential energy density can also be written as the half of the product of stress and respective strain in the material. And this is the expression you should keep in mind, and the units we use as joule per meter cube for calculation or measurement of this elastic potential energy density. Either of these relations you can use, half of square of stress by Young modulus or half of stress multiplied by strain. Either of these results you can use for elastic potential energy density to be used in various numerical calculations.